All right, let's check out a few examples here with antiderivatives or integrals, but they give you conditions. Okay, so what does that mean? Well, let's take a look. If we were given this derivative here, right? If I know the derivative and I want the antiderivative, then I am asking for the integral. And also, we could rewrite this, right? If c prime of x is this, that is equivalent to saying, well, the original function is the integral of that with respect to x. And it's good practice to put parentheses here. Some authors, some professors do it, some don't. Sometimes I'll forget, and honestly, when I'm in a single variable calculus, right, I only have x's here. When I write dx, it's assumed that it's the entire function there that we wrote. Okay, anyways, that first part is asking this. We will get to the rest of this here in just a second. So if I want the original function, that's how I am taking this approach, right? I need to integrate that derivative they give us. So we get 9x to the third over 3 minus 20x squared over 2. Remember, when you integrate, plus c. Okay? Well, I could reduce that a little bit. 9 over 3 is x to the third. 20 over 2 is 10 plus c. Now, this condition, though, tells me because, okay, let me backtrack 1 second. I didn't write the left-hand side, right? C of x. Often, if you don't write it, then it's implied that this is everything on the right. Okay, but I wanted to write that because I'm going to need that notation for the next step. What I underlined in red there tells me if I plug in x, right, I get this value of 2500. So if I plug in 10 for x, I get 2500. So going back to the function we just found, c of 10 is 2500, right? So let's stick with red. So it's telling me I will get 2500 if I plug in 10 for x. Wherever I see an x, I need to write a 10 there. Minus 10. So I'm leaving the function in all the function that I got in blue, but I'm substituting in red the values I get for c of 10, right? Just to kind of show where this came from. So anywhere there was an x, I plug 10 in. The c of x is my c of 10, I know is 2500 from that given information. So why do we need this? Well, because I want to know what c actually is. I want the function. I could find this function because I know this value here. So now we multiply this all out. So this would be 10 to the third, which is 1,000, right? Minus 10 times 100, which is 1,000, plus c equals 2,500. Well, 1,000 minus 1,000 is 0, so we get c equals 2,500. So the particular, so what does that mean? Well, the particular antiderivative means, like, what is this function, right? Like, I have enough information to find the entire function. I don't need to leave this plus c. I don't need to leave the constant. It's not unknown because I'm given information to finish it out. So x to the third minus 10x squared plus 2500 because that is the c value we just found, right? So that is the particular antiderivative. That is our particular solution, given the fact that I knew c of 10 was 2500. Be careful. Don't always just assume that this number here, it will be this number here. Okay, that is not true. This particular problem just happened to be that same value. Okay, it can happen. All right, let's move on to this next one. So, excuse me. Remember, a derivative can be written as c prime. It can also be written as dy over dt or dy dx, whatever your variable is. And when it's written in this form, really what that is saying is this, right? Like it's not that multiplication holds, but it does work. So if I would think of multiplying by dt on both sides, and why is that important? Because now we're kind of back to the introduction of what an integral means, how to do antiderivatives. So if I have integral 6et minus 7 dt, then I am finding the original function. Integral of 6et, remember, just like derivatives, you can integrate over subtraction or addition. So this would be equivalent to doing the integral of 6et, which is 6et, right? That's the easiest derivative and integral that exists. And the integral of negative 7 is negative 7t. I don't know the constant yet, but they gave me this information here. So I'm going to use that to finish out the problem. Sometimes they will say, instead of like satisfies the given condition, if the x is 0, or the variable, in this case t, is 0, often they will just say the initial condition, because that's the start, right? They're saying substitute 0 in for your variable and you'll get some sort of value. In this particular problem, the initial condition is also 0. Okay? Not always, just like the other one, we just happen to get 2500. All right, this one, that's saying if you plug in 0 for t, you will get 0 for y. All right, so let's use that. I know I get 0 when I substitute 0 in for t. Just like the last one, like it just had a coincidence. Well, don't assume your c is 0. And this one, especially when there's e's, because e to the 0 is not 0, right? That's 1. So e to the 0 is 1. Now, minus 7 times 0 is in fact 0, right? We don't need that. But now I have 0 equals 6 plus c. So c is negative 6. Just like that last problem, I caution, don't assume that is that value, right? This one I probably would have guessed, actually, because the variable is 0, we do get 0, but we don't. So the final answer is y equals 6e to the t minus 7t, and then substitute negative 6 in for c, right? That is my c, that's what I just got. So that is the particular antiderivative if that initial condition was provided. If I knew it started at 0, that's my function. All right. One more example, just because the wording is slightly different, right? We're finding an equation of the curve, so not necessarily a line, it might be, but of the curve that passes through this point. Remember that means this is x and this is y. If the slope, so again, slope means derivative, right? If it's a linear function, yes, it's m, but it may or may not be. So our slope, our derivative, is given by this. So again, we want to kind of think of moving that dx over first. So if that's the derivative, and I'm going backwards because I'm trying to find the original equation, right, the equation, then I'm going to integrate. So therefore y equals 12x to the third over 3 minus 12x squared over 2 plus c. Before we move forward, let's reduce. Always reduce, make it easier. 4x to the third minus 6x squared plus c. All right, now we have this information. We have the 0.13, right? That is a condition. Just like the other problems where it said, given this condition, we could have wrote this as y of 1 equals 3, right? That means if x is 1, we get y is 3. So substitute all your values you were given. Y is 3. I'm going to just write this x is 1. So 4 multiplied by 1 to the third minus 6 times 1 squared plus c. All right, so we get 3 equals 4 minus 6 plus c. That is a negative 2. So I'm going to add 2 to the other side. 5 equals c. Okay. Well, if 5 is c, I now have enough to write the equation of the curve. Right? This was our equation, but we still had to find c. So therefore, y equals 4x to the third minus 6x squared plus 5. Again, because 5 is c, now I know the entire equation of the curve. And again, you could always check, right? Do your derivative and make sure it comes out. We didn't do that for the others, so let's go ahead and do it really quick. Y prime, or dy dx, right? Same notation. If I do derivative, I get 12x squared minus 12x, and that derivative of 5 is 0. Okay, works out. I know that the 1, 3 checked out to get the equation, and I know that the derivative of my final answer is the given value, right? The question. Good to go.